Might need to make a section leader duty reminding me to hit record every day. Here's the link in both of these. Okay. Okay, so moving on to chapter 14. You should have done a reading quiz on this before class, so hopefully this is not too unfamiliar to you. So now we're going to talk about how we actually structure these file systems in physical space. So what are the data structures that we use to maintain the file system, and what are some of the trade-offs in terms of implementing these? So first off, since we did skip over storage systems, so I think that's a little more relevant for like an architecture course probably. I wanted to just give a quick overview of the technologies that we're looking at here that sort of go under our file system, because some of these properties are somewhat useful to think about whenever we're talking about how to actually implement the file system, and how this actually works. So we have basically two things that we might use for mass storage. This may change in the future, that we'll have other types of underlying technology. There have been a lot of developments in terms of other non-volatile memories that are not what we're looking at here. So there's resistive RAM. There's MRAM, which is magnetic RAM. There's Intel Optane, which I think a variant of that. So there are quite a few different types of non-volatile memory that I'm not going to list here that may be beneficial to use as mass storage in the future. As of right now, they're a little bit too small to be able to use. But this is something that eventually might be a new alternative to these two, would sort of add again more things, more columns in this chart to be give you an option for what you would use for a system. So as of right now, you're mostly restricted to disks or non-volatile memory, and non-volatile memory being flash for secondary storage. So usually this is going to be the difference between HDD or SSD. So if you're building or buying a computer system, this is what you're looking at whenever you're purchasing a hard drive or looking at the hard drive on that system. So hard drives, the technology behind them is a spinning magnetic disk. So there is a sort of an arm that reads from that disk. It's similar to some extent to like a CD player, where you're sort of moving around. It rotates. You're able to sort of pinpoint where the file is on this disk, and then read the magnetic state, where either absence or presence of magnetism is going to indicate a 1 or a 0. And these can be pretty dense based on the technology that we have to be able to sort of encode a lot of information in a single space. And we can have sort of setups where we have multiple of these spinning magnetic disks and multiple arms, and be able to read from multiple places at the same time. So we can sort of make it even more dense by adding additional disks, additional arms to be able to read from them. Then we have solid state drives. The technology behind that is called NAND flash. So this is it's basically based on NAND gates, and it's all comprised of transistors. So there are no moving parts here. It's just electronics. And this means that everything is sort of managed by a charge. So in a hard disk drive, the way reads and writes work is we have this actuator arm with a read write head that moves to the correct sector and checks for charge. So checking for magnetic charge by sort of moving this arm to the proper sector, the proper place on the disk that we're trying to read or write from, and then that gives you the value that's stored there. NAND flash is just going to read the existing charge or send a charge to alter the state. So here, because it's just transistors, we basically just send a new charge through. This, raises the charge, and then that allows us to sort of read what the state is. But again, this is sort of no moving parts. It's just transistor based. So it's really just electronics that manage the solid state drives. So there are benefits and sort of downsides to both of these. The main benefit to a hard disk drive, if you've built a computer or looked into these, the biggest advantage of HDDs these days is that they are less expensive per byte. So an SSD of an equivalent size to an HDD will be much more expensive per byte than that HDD. So you can get a lot more space in a hard disk drive than you can in an SSD for the same value. Just because HDDs have been around for longer, so I think the manufacturing processes are probably more in place. It's easier to sort of continue packing more bytes onto them, and it's a little cheaper to manufacture. So that's the main benefit of HDDs. Big benefits of SSDs are because it's just transistors and there are no moving parts. They generally are lower latency. They generally use less energy, and they're generally more compact. So a lot of the time, if you purchase a laptop will probably nowadays not come with an HDD at all. It'll just come with an SSD because we can make them a little bit more compact. It doesn't have to have this circular disk that has to fit inside that computer, or multiple circular disks that have to have some amount of space for vertical stacking. So most of the drives in your phone, the drive in your computer, anything that's small is probably an SSD because it is going to be more compact and it's going to be lower latency. So for things like your phone, where you want it to boot up quickly, you want to be able to open applications quickly, reads and writes to and from the SSD are going to be a lot faster and a little more energy efficient. So in mobile environments, you really want to have an SSD instead of an HDD. So other cons of both of these. So for hard disk drive, obviously we just talked about the latency difference. So because there is a moving part, it's higher latency to read and write. And the other issue is that mechanical parts can fail. So if you're not sort of careful about moving around a system with an HDD in it, this can cause the mechanical parts that are moving while you're moving the system, that can cause them to fail. So generally you see these in like servers where the disk is not going to move while it's operational. In desktop computers where again the disk is not going to move while it's operational. Early on laptops, my wife's MacBook, this is early like 2010 maybe, around then, her MacBook started to fail because the hard drive went bad from the fact that she would like have the laptop on and carry the laptop from office to the living room or something like that. And because of moving this laptop while it was operational, the hard drive eventually failed because some of the mechanical parts got out of position or were damaged due to the fact that it was moving while it was moving internally. So this was an issue with early laptops, and why at this point these have all been replaced with SSDs. And then the final disadvantage to SSDs that we touched on a little bit here, but not sort of in depth, is that there is a limit to the number of writes that can be performed in an SSD. So they have what's called a wear down factor, where the transistors that are used here, the flash memory, has a limit to how many times it can be rewritten before the circuits start to wear down and sort of lose the checking, or the ability to check for charge in that SSD. So we have to be a little bit careful with how we use SSDs in terms of the number of writes that we perform, especially. And this is why that the SSDs will not perform swapping. or that systems that have an SSD will try not to do swapping on that SSD. Because if we try to swap memory out for paging, that means that we're writing a lot to that SSD, and that means that we're sort of wearing it out unnecessarily. So generally, you know, what you kind of want in a desktop system or in a server system is you kind of want like an SSD to be able to boot up to or to load programs from, have the things that you want very low latency for on that SSD, and then you want an HDD to be able to be your swap space and to do some things, you know, like mass storage, to have a little more space and be able to write to it more frequently. Of course, the latency issue means that, like, technically speaking, you might want the SSD for swap space because it's faster, and so storing things into it and loading things back from it would be quicker for paging. But the limit to the number of writes makes that sort of infeasible because we'll very quickly wear out an SSD if we use it as swap space. So any questions on sort of the setup here? I just wanted to give a quick overview since we did skip over those chapters. Once I touched it with a magnet and broke it. Yeah. So yeah, hard drives, due to the magnetism of the sort of platters, you could also, you know, you used to be able to sort of erase these by touching them with a magnet. I don't think SSDs have the same problem. Someone correct me if I'm wrong there. Some of the newer memories do have that issue. So we've been looking at MRAM, and since that is also magnetic RAM, if you take a magnet and run it over that, if you take a magnet and run it over it, it will, you know, it'll break an MRAM, but I don't think it'll break an SSD. So I don't think the NAND flash is, I mean, maybe like a very big magnet. A very big magnet might break it just because of the fact that, you know, it might alter the charges in some way. Yeah, a magnetic hammer. And yes, all of them, none of them are actual hammer proof. So if you really want to destroy it, you know, physical destruction is probably the best way to go. I know a lot of people sort of rely on rewriting them with zeros. So this is sort of a security aside here. That the Mjolnir, a security aside that, like, when you know, get rid of a hard drive, when you delete things on the hard drive, it doesn't actually delete the files. So it just deletes some of the stuff in these directory structures, right? And then maybe eventually garbage collects it when it needs more space. So this is why, like, if you accidentally delete a file, generally speaking, you can run an application that will just basically parse through the bytes that are still on the drive, and you can find that file. It might be difficult because it might just be, you know, an unstructured blob of data that you have to interpret as this is my file. But generally, you can still find that file on a hard drive. So it's also due to the sort of magnetic charge issue. Sometimes even if you overwrite it with zeros once, you can still get like a trace of what used to be there. And so there are tools that you can get to basically like try to zero out your hard drive better. And essentially what those do is like overwrites with zeros a bunch of times. So I think like I feel like the DoD, what's the DoD standard for overwriting a hard drive? How many times is the question? Might not be able to find it fast enough. I'll look it up for you, and we can talk about it on Monday. But there are basically standards that will, you know, define how many times you should overwrite a hard drive to ensure that the data is actually gone. And this is, you know, basically like it's something like 13 times, I think, that you overwrite it. And that way the, you know, magnetic charge is sort of sufficiently dispersed from what the original data was, that it's hard to like even physically recover it. If you, you know, if you would take something like, not oscopes, but like a physical electronic tool and sort of manually look at this, it would even be hard to recover it at that point. So. And then sort of I think the between the DoD standard and between not doing anything, there was like you could wipe it 7 times, and that was pretty good. Like that would get past most software tools that would be able to look at your data. So like if you sold your computer to someone else and they were trying to find your credit card after they got your computer, then overwriting it like 7 times was probably sufficient to prevent a low-level hacker from being able to get your data. So a little bit of a long aside, but hopefully interesting. So this is the general setup for HDDs versus SSDs or SSDs. Both of these are organized into blocks of memory, roughly 4 kilobits or kilobytes in size to a few megabytes in size, depending on the structure. These can be further divided into either what we call sectors on a disk or pages on an NVM. So the blocks are generally smaller. NVMs sort of divide the larger blocks that they have into 4 kilobyte sized pages. And the disks will divide these 4 kilobyte sized blocks that they have into smaller sectors. It's really just small design decisions here. But generally we have this 4 kilobyte sized mapping to a disk that matches the 4 kilobyte sized mapping that we have for pages and frames. So this is kind of a useful thing to have, that the blocks on disk will be roughly the same size as a page in memory, so that when we do want to read a file into memory and do memory mapped file stuff, we have roughly the same size of what we're going to put into memory, or that size exists somewhere within the system, so that we can sort of take chunks of stuff very lazily and put it into memory in that same chunk size. So there are 2 things that we sort of need to think about as we discuss file systems. Mainly, how does the file system look to the user, and how does the file system map to storage devices? So these are sort of, they pool back and forth at each other, making it convenient for the user versus making it convenient for the operating system to map to the storage devices. So this is just sort of dependent on trying to make sure that both of these conditions are satisfied, that we don't end up sort of sacrificing usability for performance and vice versa. So the book gives this document that we're going to sort of fill out together here, that shows the sort of overall hierarchy of a file system. So we have a layered approach here that allows us to make this very modular. So we could go straight from application program to the operating system to devices. And that could just be the operating system handles everything from, the file metadata, where the file exists, where that is in a block on disk, handling the fact that we're going to probably have to use a device driver since the disk might be from different sources, and then eventually getting to, running the commands, sort of managing the assembly level stuff to be able to sort of pass into the registers that exist on this I/O device. And then finally getting that data back and sending it back to the application program. So we could handle all of this in one fell swoop, but it wouldn't be very modular. It would be very difficult to sort of, substitute a new, it'd be a new device into a system that sort of has a full stack all implemented in one place. So generally speaking, we want to make this so that we want to design this so that each part of the operating system that handles files handles a slightly different part of this task. So going from the application program, the first thing that does anything is sort of the logical file system. So this is the part that manages file metadata. So all this stuff like permissions, everything that the user sort of experiences with files. So when you do ls-l, this is all part of the sort of logical file system. So it just knows about like the user level metadata and information about files. So it knows about metadata, it knows about directory structure, it knows about file structures via what we're going to talk about later as via file control blocks or FCDs, which includes a bunch of stuff. including permissions, owners, location of, and the location of file contents. Again, this is all just sort of like the user level information about these files and about the directory structure. So it's just what the user needs to know, what we need to be able to tell them so that they can interact with files, and so that applications that are run by the user can interact with files. So this is sort of the, the higher level view of the file system. This is usually what we interact with. So generally, we're not going to deal with the lower levels here. We're just going to deal with the sort of high level logical file system that our applications run on. Then we have the file organization module. So this knows about the next level down. So the next level down from here is we have the sort of metadata. We know where the directories are. We know what names are. We know sort of all the stuff we need to access files as an application. But next we need to know like where these actually are in the storage. So the file organization module knows about files and logical blocks and tracks unallocated blocks. This sort of knows about the generic structure of the underlying file system. So it knows about the fact that there is memory organized into block sizes. It knows about the actual like file inodes that we'll talk about a bit later. So, it knows about the physical structure of the files on the system, and it knows about free blocks that are available for files. So we'll be able to, basically create more space by using these unallocated blocks or create new files using those unallocated blocks. So it knows a bit more about the physical structure of the disk, but it knows about that at sort of a high level still. So it really just knows about open space, but it doesn't know how to like store something into that space or get something from that space. It just knows about the fact that that space exists and can be used. Then next level, we have the basic file system. So this issues generic commands on device drivers, or to device drivers, to read and write blocks on the storage device. And it also manages buffers and caches. So caches in this case are not like the hardware caches that we talk about with DRAM. So those are not managed. The DRAM sort of associated caches are not managed by the operating system. That's all managed by hardware. In this case, this is more of like, I don't know if you learned this term in data structures or not, but memoization. So when you sort of compute a result and you record the intermediate result. So if you're computing the Fibonacci problem, for example, you're going to do 1 plus 1 plus 1 plus 2 plus 2 plus 3 plus 3 plus 4 or 3 plus 5. You can record basically the intermediate results there. And sometimes you can basically just replace the two numbers that you're about to add with the result that you already computed from a previous round of that. And this is true for a lot of problems in computer science. This is essentially the same thing. So we're just kind of remembering, like, I did access this file at some point. It had these logical blocks, and this is where they were. It had, this file control block maybe, which had these permissions. So basically, save some of the information from the upper parts of the file system, so the logical and file organization module parts, in a cache, so that whenever we go to access something, we can kind of skip around a bunch of loading and storing stuff from memory if we've recently accessed this. So this is trying to make repeated accesses to the same file quick. But this is all sort of, software managed caches. So this is, at best going to be in DRAM. It's not a hardware thing generally. These are going to be stored in. We can have hardware caches for this if we wanted to. But this is already sort of like at the point that it's pretty slow if we're accessing disk. So it's not hugely beneficial to have all of that, caching be implemented in transistors when eventually we're just going to end up accessing a disk anyways. So, RAM is sort of fast enough, or relying on the general memory hierarchy of the system is okay here. So that is, what sort of has generic commands to device drivers, but not actually the device drivers themselves. So this might be the point that we're saying, like, read from this device, this block on that device, or this block number on that device, or write to this block number on this device. And so we need one lower level, which is the actual device driver and interrupt handlers to transfer information between main memory and the storage devices. So this is, the basically like memory to storage copying that happens at the device level. So those of you who took, 361 already, this would be the sort of, last thing that we talked about in there, which is, memory to memory copying. You set up some registers using the device drive. The device drivers are going to set up some registers that say, like, take memory from this address in RAM, put it at this block in storage, or this address in storage. So this is sort of, the specific information about how to handle this device, where the things need to be placed in the device, what the configuration is for that device, so that, maybe we set some bits to say it's time to start this transfer. And that's what the IO control level handles, is like sort of the device specific information where, we have a manual. The manual tells us that we need to set these bits properly for it to work. And that's what we set at this level. So this is the sort of low level details of how the actual device works. And this allows us to be very modular, because we can write a device driver that is for, the USB key that I'm plugging into my system. And that's different from the SSD that I already have attached, or the HDD that's already attached. Those can all have sort of vendor specific device drivers and interrupt handlers, as long as they match the basic file system commands, or that the basic file system commands can interact with them. We can, sort of substitute devices at will, and we can copy files in the same way and sort of have the same upper level view of it, but different devices under the covers. Okay. So that is the sort of general layered structure of the filed system, going from sort of the top level down to the bottom level for devices. We then need to talk about a couple things, again, that are sort of integral to the implementation of the file system before we get into how they're actually implemented. So just basically terms that we need to know for the rest of the chapter here. So first is the boot control block. So the boot control block is the information needed to boot the operating system from a volume, from a disk, let's say. This is empty if the disk does not contain an OS. So this is necessary for your computer to boot up. This is usually managed by like the BIOS, or not managed by the BIOS, but it'll be like written when you install the operating system, and the BIOS will know where to find this and how to target that to boot up your operating system. It is, roughly the same for every operating system, for each BIOS, for each, system setup. So BIOS is the old version. You'll see sometimes in newer systems what's called UEFI, which is sort of a scripting language for booting systems. So you define where the operating system is, where it starts, what commands you need to run to boot that operating system. But this is the first thing that gets hit whenever you start up the system. So we have the BIOS, and then it calls this boot control block and is able to boot up the operating system. So if we don't have an operating system on a disk, this part is empty. And it just doesn't have anything there because we don't need to boot an operating system from that disk. So this keeps us, allows us, one, if we want to have different operating systems booting from different volumes, we can. Otherwise, we can have a boot control block that sort of directs to different operating systems. So applications like Grub, if you've ever used a Linux system, there's a tool called Grub that sort of knows where all of the different things that you might want to boot are, and then it can boot those from a screen. So Grub would be the thing in the boot control block then, so it loads itself, and then from there it can load your OS. So this can be not an operating system as well. It can be like a bootloader itself that sort of boots from there. But generally, we have this so that we know where to boot the OS from, so we can sort of bootstrap the system and get it going. We then have the volume control block. So this records number of blocks, number of free blocks, size of blocks, and file control block information. This is really just the block control block, essentially. It's just recording all of the information about the storage that we need to use as part of the sort of organization module here. This is all information that we would track sort of at that level of the system. Then we have the file control block, which is all of the file permissions, file dates, data blocks, and pointers. So this is the sort of logical file system level information. It's not necessarily stored at that level. It might be stored in the file organization module, but this is what is used by the logical file systems. We have all these permissions, dates, data blocks, all the stuff that we have to know about in terms of where that file is and what we can do with that file in this system. The mount table, this contains information about mounted volumes. I'm going to add in here from some links that we have the mount and unmount commands. So the mount and unmount commands are sort of allow you to be able to pull a new drive into your file system. So this maps from a device to a place in the file system. So generally, they have this command listed here. That you have all these options that you can provide, and you're going to say the device name, and then you're going to say the directory name. So usually, the OS handles this for you, right? If you plug in a USB drive to your Windows system, eventually it'll just show up as drive D. Or if you do it for a Linux system, it'll show up as some folder, /USB/ something, maybe. So this mount command is what's sort of happening under the covers there. So when you load this up, it gets a device name from the lower level drivers, and then it is able to run mount that device name to drive D. And so that allows it to actually appear in your operating system and you to be able to access the files as if they are other files in the system. So this sort of implants the logical file system onto or puts this drive into the logical file system. So it kind of bridges the gap between this lower level stuff that's happening here with the upper level that the user is experiencing. And this is something that, like, if you're using command line Linux on like a server or something like that, and you attach a drive, that you have to do this manually because it won't manually do it for you. That you do have to mount a device to a directory to be able to copy files from it or save files to it. So this is a sort of a good command to know in case you ever have to work with a Linux command line interface. And then to get rid of the device so it doesn't yell at you when you unplug your USB without unmounting it, and Windows complains that it might damage the USB, which it doesn't, but it'll still complain just in case you were in the middle of copying a file or something when you unplugged it. Unmounting is just taking the directory or device and removing it from the system. And I'm not sure why they felt the need to save like one character on umount rather than just saying unmount, which to me would have made a lot more sense. But I'm not Linus, so I don't know, maybe it's a huge issue. So yeah, mounting a disk adds it to the logical file system for a user to access. And the mount table would contain the information that allows us to sort of maintain those mappings, remember where everything is mapped to. The directory structure cache, we talked about that a little bit already. So this is managed by the basic file system. So this is the recently accessed directory information for quick access. So just to make sure that we can re-access things quickly. And then we have two more things to talk about, and then we'll be done for the day. So the system open file table and the process open file table. So we have two different places that we maintain information about open files in the system. So the first one here is the system open file table. So this contains a copy of the file control block for each open file. And the notes further go into, or the book sort of further goes into the process of like how file opens work then. So we'll discuss that in a second here. I just want to leave a placeholder. And then we have the process open file table, which contains a pointer to the system-wide open file table for all open processes in a process. This contains read and write pointers for each file, and we call these entries. So entries in the file table, or the open file table, are called file descriptors. So FD in Unix, in a lot of the code that you read from Linux system, from the C standard library, you'll see int FD for int file descriptor, or you'll have file star FD for file descriptor. It's a common abbreviation for variable names in Linux, or you'll have file handles in Windows. So both same thing, it's just a pointer to the system-wide open file table. And this allows us to save some information in that system-wide table and sort of reuse it for different processes that might be using the same files. So the system open file table, it manages all of these actual files. So when we open a file, on file open, we search this table for the FCB for the file. So we don't search the process open file table, we're searching the system open file table. If the process already has this open, we can quickly find that it has a pointer to that file, but we can't open it multiple times sort of by the same process because it's just a pointer to this system open file table. So we can have multiple pointers if we want to from a process. So we search the system open file table for the file. If it exists, we make a pointer to it in the per process table. If not, we find the file in the directory. To it in the per process table. And this way we're able to sort of maintain this system-wide mapping of or basically just keep the information about like the logical file system, and then any information we need to know about the for the file organization module, we can keep this in the system open file table. So we have the logical information is sort of maintained once. So all the permission stuff, all of this other stuff, we don't have to replicate for every single process. We can just have a pointer to that information in each process, and then that pointer can lead us to all of the other information that we need. So this keeps us from sort of duplicating all of that extra metadata every time we open a file in a different process. These may be kind of unique entries if all the processes are using different files, but often there's some sharing in the system, and that means we can only have certain files open, or a limited number of files open in the system open file table. Okay, so any questions about the material from today? Otherwise, we will pick up on 14.3 and 14.4 on Monday, and then we'll probably finish off the rest of this chapter on Wednesday and move on to some special topic on Friday. Any questions? Okay, in that case, have a great weekend, and I will see you on Monday.
Thanks, Professor.
Thank you, Professor.